The Busy Beaver game consists of designating a halting, binary alphabet Turing machine which writes the most 1s on the tape, using only a limited set of states. The rules for the two-state game are as follows. The machine must have two states in addition to the halting state, and the tape starts with 0s only. As the player, you should conceive each state aiming for the maximum output of 1s on the tape while making sure the machine will halt eventually. The nth Busy Beaver, BBN, or simply Busy Beaver, is the Turing machine that wins the end-state Busy Beaver game. That is, it attains the maximum number of 1s among all other possible end-state competing Turing machines. The BB2 Turing machine, for instance, achieves 4 1s in 6 steps. The Busy Beaver game has implications in computability theory, the halting problem, and complexity theory. The concept was first introduced by Rado in his 1962 paper on non-computable functions. The end-state Busy Beaver game, introduced in Rado's 1962 paper, involves a class of Turing machines, each member of which is required to meet the following design specifications. The machine has n operational states plus a halt state, where n is a positive integer, and one of the n states is distinguished as the starting state. The machine uses a single two-way infinite tape. The tape alphabet is 0, 1, with 0 serving as the blank symbol. The machine's transition function takes two inputs: the current non-halt state, the symbol in the current tape cell, and produces three outputs: a symbol to write over the one in the current tape cell, a direction to move, and a state to transition into. There are thus n-state Turing machines meeting this definition. The transition function may be seen as a finite table of 5 tuples, each of the form running. The machine consists of starting in the starting state, with the current tape cell being any cell of a blank tape, and then iterating the transition function until the halt state is entered. If, and only if, the machine eventually halts, then the number of 1s finally remaining on the tape is called the machine's score. The end-state Busy Beaver game is a contest to find such an end-state Turing machine having the largest possible score, the largest number of 1s on its tape after halting. A machine that attains the largest possible score among all end-state Turing machines is called an end-state Busy Beaver, and a machine whose score is merely the highest so far attained is called the champion end-state machine. Rado required that each machine entered in the contest be accompanied by a statement of the exact number of steps it takes to reach the halt state, thus allowing the score of each entry to be verified by running the machine for the stated number of steps. Related functions. The Busy Beaver function sigma. The Busy Beaver function quantifies the maximum score attainable by a Busy Beaver on a given measure. This is a non-computable function. In fact, a Busy Beaver function can be shown to grow faster asymptotically than does any computable function. The Busy Beaver function, NN, is defined such that sigma is the maximum attainable score among all halting two-symbol end-state Turing machines of the above described type. When started on a blank tape, it is clear that sigma is a well-defined function. This infinite sequence sigma is the Busy Beaver function, and any end-state two-symbol Turing machine M for which sigma equals sigma is called a Busy Beaver. Note that for each n, there exist at least two end-state Busy Beavers. Non-computability. Rado's 1962 paper proved that if f is any computable function, then sigma greater than f for all sufficiently large n, and hence that sigma is not a computable function. Moreover, this implies that it is undecidable by a general algorithm whether an arbitrary Turing machine is a Busy Beaver. Even though sigma is an uncomputable function, there are some small n for which it is possible to obtain its values and prove that they are correct. It is not hard to show that sigma equals 0, sigma equals 1, sigma equals 4, and with progressively more difficulty it can be shown that sigma equals 6 and sigma equals 13. Sigma has not yet been determined for any instance of n greater than 4, although lower bounds have been established. Complexity and unprovability of sigma. A variant of Kolmogorov complexity is defined as follows. Cf. Boulos, Burgess and Jeffrey, 2007. The complexity of a number n is the smallest number of states needed for a BB-class Turing machine that halts with a single block of n consecutive 1s. On an initially blank tape, the corresponding variant of Chaitin's incompleteness theorem states that, in the context of a given axiomatic system for the natural numbers, there exists a number k such that no specific number can be proved to have complexity greater than k, and hence that no specific upper bound can be proven for sigma, were proved, as mentioned in the cited reference. For any axiomatic system of ordinary mathematics, the least value k for which this is true is far less than 10. Consequently, in the context of ordinary mathematics, neither the value nor any upper bound of sigma can be proven equals n, and there are infinitely many true but unprovable sentences of the form sigma less than n. Max shifts function s in addition to the function sigma. Rado, 1962, introduced another extreme function for the BB class of Turing machines, the maximum shifts function s, defined as follows. The number of shifts m makes before halting, for any m in n. The largest number of shifts made by any halting n-state two-symbol Turing machine, because these Turing machines are required to have a shift in each and every transition or step. The max shifts function is at the same time a max steps function. Rado showed that S is non-computable for the same reason that sigma is non-computable. It grows faster than any computable function. He proved this simply by noting that for each n, S sigma, because of shift is required to write a 1 on the tape. Consequently, S grows at least as fast as sigma, which had already been proved to grow faster than any computable function. The following connection between sigma and S was used by Lin and Rado, Computer Studies of Turing Machine Problems, 1965, to prove that sigma equals 6. For a given n, if S is known, then all n-state Turing machines can be run for up to S steps, at which point any machine that hasn't yet halted will never halt. At that point, by observing which machines have halted with the most 1s on the tape, one obtains from their tapes the value of sigma. The approach used by Lin and Rado for the case of n equals 3 was to conjecture that S equals 21, then to simulate all the essentially different three-state machines for up to 21 steps. By analyzing the behavior of the machines that had not halted within 21 steps, they succeeded in showing that none of those machines would ever halt, thus proving the conjecture that S equals 21, and determining that sigma equals 6 by the procedure just described. Inequalities relating sigma and S include the following, which are valid for all n1, and an asymptotically improved bound. There exists a constant c, such that for all n2, known values for sigma and s, the function values for sigma and s are only known exactly for n less than 5. The current 5-state busy Beaver champion produces 4,098 1s, using 47,176,870 steps. But there remain about 40 machines with non-regular behavior which are believed to never halt, but which have not yet been proven to run infinitely. At the moment, the record 6-state champion produces over 1,018,267 1s, using over 1,036,534 steps. As noted above, these are two-symbol Turing machines. Milton Green, in his 1964 paper, A Lower Bound on Rado's Sigma Function for Binary Turing Machines, constructed a set of Turing machines demonstrating that where is math up arrow notation and A is Ackermann's function. Thus, and where the number G1 is the enormous starting value in the sequence that defines Graham's number. In contrast, the current bound on sigma is 1,018,267, which is greater than the lower bound 33 equals 27. In fact, it is much greater than the lower bound, which is Green's bound 4. Proof for uncomputability of S and sigma. Suppose that S is a computable function and let evals denote a trademark. Evaluating S. Given a tape with N1S, it will produce S1S on the tape and then halt. Let clean denote a Turing machine cleaning the sequence of 1S initially written on the tape. Let double denote a Turing machine evaluating function n plus n. Given a tape with N1S, it will produce 2N1S on the tape and then halt. Let us create the composition double evals clean and let N0 be the number of states of this machine. Let create underscore N0 denote a Turing machine creating N01S on an initially blank tape. This machine may be constructed in a trivial manner to have N0 states. Let n denote the sum N0 plus N0. Let BADS denote the composition create underscore N0 double evals clean. Notice that this machine has n states. Starting with an initially blank tape, it first creates a sequence of N01S and then doubles it, producing a sequence of N1S. Then BADS will produce S1S on tape, and at last it will clear all 1S and then halt. But the phase of cleaning will continue at least S steps, so the time of working of BADS is strictly greater than S, which contradicts to the definition of the function S. The uncomputability of sigma may be proved in a similar way. In the above proof, one must exchange the machine evals with eval sigma and clean with increment, a simple trademark, searching for a first zero on the tape and replacing it with 1. The uncomputability of S can also be established by reference to the blank tape halting problem. The blank tape halting problem is the problem of deciding for any Turing machine whether or not it will halt when started on an empty tape. The blank tape halting problem is equivalent to the standard halting problem, and so it is also uncomputable. If S was computable, then we could solve the blank tape halting problem simply by running any given Turing machine with n states for S steps. If it has still not halted, it never will. So, since the blank tape halting problem is not computable, it follows that S must likewise be uncomputable. Exact values and lower bounds. The following table lists the exact values and some known lower bounds for S and sigma for the generalized busy beaver problems. Known exact values are shown as plain integers, and known lower bounds are preceded by a greater than or equal to symbol. Note: entries listed as are bounded from below by the maximum of all entries to left and above. These machines either haven't been investigated or were subsequently surpassed by a machine preceding them. The Turing machines that achieve these values are available on both Heine Markson's and Pascal Michel's web pages. Each of these websites also contains some analysis of the Turing machines and references to the proofs of the exact values. Values of S. Values of sigma. Generalizations for any model of computation. There exist simple analogues of the busy beaver. For example, the generalization to Turing machines with n states and m symbols defines the following generalized busy beaver functions. Sigma, the largest number of non-zeros printable by an n-state, m-symbol machine started on an initially blank tape before halting, and S, the largest number of steps taken by an n-state, m-symbol machine started on an initially blank tape before halting. For example, the longest-running 3-state 3-symbol machine found so far runs 119,112,334,170,342,540 steps before halting. The longest-running 6th state two-symbol machine, which has the additional property of reversing the tape value at each step, produces 6,147 1s after 47,339,970 steps. So SRTM 47,339,970 and sigma RTM 6,147. It is possible to further generalize the busy Beaver function by extending to more than one dimension. Likewise, we could define an analog to the sigma function for register machines as the largest number which can be present in any register on halting, for a given number of instructions. Applications. In addition to posing a rather challenging mathematical game, the busy Beaver functions offer an entirely new approach to solving pure mathematics problems. Many open problems in mathematics could, in theory, but not in practice, be solved in a systematic way given the value of S for a sufficiently large n. Consider any conjecture that could be disproven via a counterexample among the countable number of cases. Write a computer program that sequentially tests this conjecture for increasing values. In the case of Goldbach's conjecture, we would consider every even number 4 sequentially and test whether or not it is the sum of two prime numbers. Suppose this program is simulated on an n-state Turing machine. If it finds a counterexample, it halts and notifies us. However, if the conjecture is true, then our program will never halt. Now, this program is simulated by an n-state Turing machine. So if we know S, we can decide whether or not it will ever halt by simply running the machine that many steps. And if, after S steps, the machine does not halt, we know that it never will, and thus that there are no counterexamples to the given conjecture. This would prove the conjecture to be true. Thus, specific values for S could be used to systematically solve many open problems in mathematics. However, current results on the busy Beaver problem suggest that this will not be practical for two reasons. It is extremely hard to prove values for the busy Beaver function. It has only been proven for extremely small machines with fewer than 5 states, while one would presumably need at least 20 to 50 states to make a useful machine. Furthermore, every known exact value of S was proven by enumerating every n-state Turing machine and proving whether or not each halts. One would have to calculate S by some less direct method for it to actually be useful. But even if one did find a better way to calculate S, the values of the busy Beaver function get very large, very fast. S greater than 1,036,534 already requires special pattern-based acceleration to be able to simulate a completion. Likewise, we know that is a gigantic number. Thus, even if we knew, say, S, it is completely unreasonable to run any machine that number of steps. There is not enough computational capacity in the known universe to have performed even S operations directly. Examples. These are tables of rules for the Turing machines that generate sigma and S, sigma and S, sigma, sigma and S, and the best known lower bound for sigma and S, and sigma and S. In the tables, columns represent the current state and rows represent the current symbol read from the tape. Each table entry is a string of 3 characters, indicating the symbol to write onto the tape, the direction to move, and the new state. The halt state is shown as H. Each machine begins in state A with an infinite tape that contains all 0s. Thus, the initial symbol read from the tape is a 0. Result key. Result. 00100 result. 0011110 result. 001111100. Unlike the previous machines, this one is a busy Beaver only for sigma, but not for ES. Equals 21, result. 00101111111111110 result. 4098 1 S with 8191 0 S interspersed in 47,176,870 steps. Result. 3.515 times 1,018,267, 1 s in 7.412 times 1,036,534 steps.